Hey future physicists, have you ever wondered how a car engine works? Or why no engine is 100% efficient? Well, that's because engines can never convert all heat energy into work, but there's an ideal engine that tells us the theoretical maximum efficiency possible. This perfect engine is called the Carnot engine, named after the brilliant Sadi Carnot. The Carnot engine is theoretical, but it helps us understand how real heat engines work. It operates between two temperature reservoirs, a hot reservoir at T_H and a cold reservoir at T_C. The cool thing about the Carnot engine is that it's reversible, meaning it can work in both directions, and that's what makes it an ideal model for understanding the limits of efficiency. Alright, let's break down how the Carnot engine works. It runs in a cycle made of two isothermal, constant temperature processes and two adiabatic, no heat exchange processes. Here's how. In the isothermal expansion, the gas inside the engine absorbs heat, Q_H, from the hot reservoir, all while keeping its temperature constant at T_H. During the adiabatic expansion, the gas does work on the surroundings and cools down as it expands since no heat is exchanged. The process then flips for compression. The gas rejects heat, Q_C, during the isothermal compression while staying at the cold reservoir temperature, T_C, and finally undergoes adiabatic compression, where work is done on the gas, increasing its temperature. Now, you might be wondering, how do we measure the efficiency of this ideal engine? The Carnot engine gives us the maximum possible efficiency that any heat engine can achieve. And guess what? It all comes down to the temperature difference between the hot and cold reservoirs. The efficiency of the Carnot engine is given by this formula, 1 minus T_C by T_H, where T_H is the temperature of the hot reservoir in Kelvin, T_C is the temperature of the cold reservoir in Kelvin. This tells us that the higher the temperature of the hot reservoir and the lower the temperature of the cold reservoir, the more efficient the engine becomes. Let's talk about the heat transfer and work involved. During the Carnot cycle, heat is absorbed from the hot reservoir during the isothermal expansion process, and heat is rejected during the isothermal compression. The work done by the engine is the difference between these two heat transfers, W equals Q_H minus Q_C. This work is what powers the engine and allows it to perform tasks like turning the wheels of a car. In fact, the work done is directly proportional to the efficiency and is given by the equation W equals Q_H times 1 minus T_C by T_H. This means that the work the engine does depends on the heat absorbed and the temperature difference between the hot and cold reservoirs. Let's solidify these concepts with a real-world example. Imagine a Carnot engine operating between a hot reservoir at T_H equals 500 Kelvin and a cold reservoir at T_C equals 300 Kelvin. The engine absorbs Q_H equals 2000 joules of heat. Let's calculate the work done by the engine. Here's the formula we'll use. W equals Q_H times the quantity 1 minus T_C divided by T_H. Now, substitute the given values. W equals 2000 times the quantity 1 minus 300 divided by 500, which is 2000 times 0.4. So, the work done by the engine is 800 joules. This is how much useful work the engine can perform based on the heat it absorbs and the temperatures of the reservoirs. So to wrap it up, the Carnot engine is an idealized heat engine that tells us the theoretical maximum efficiency that can be achieved by any engine. Its efficiency depends on the temperatures of the hot and cold reservoirs and is given by the equation 1 minus T_C by T_H. It operates in a cyclic process involving isothermal and adiabatic steps, with heat absorbed from the hot reservoir and rejected to the cold reservoir. The work done by the engine depends on the difference between the heat absorbed and the heat rejected. The Carnot engine sets the ultimate benchmark for the performance of real-world heat engines. Next time you look at a car engine or a refrigerator, remember that the Carnot engine is the gold standard for efficiency, even though real engines can't quite reach its ideal performance. Keep exploring and see how these concepts apply to everything around us in the world of thermodynamics.